In this lesson, we're going to be looking at Objective 3.3, Solids, Liquids, and Gases. The objective states that we should be able to represent the differences between solid, liquid, and gas phases using a particulate level model. So let's just start off with solids. So we have two different types of solid structures. We have a crystalline solid and a amorphous solid. So crystalline solids are going to be considered the more ordered structure compared to amorphous. When we look at the arrangement of particles, we're looking at a regular and repeating pattern in the solid. Generally with crystalline, it's going to have a defined melting point, as well as it's going to be more rigid, meaning that it's going to be a lot stronger than amorphous. Some examples that you can think of, diamond is a good one. All of our metals are going to be in these ordered structures, table salt, etc. Okay. And then next, amorphous solids will be an unordered structure, while its arrangement of particles will be in an irregular pattern in the solid. So kind of going off of crystalline, it does not have a defined melting point. I'll talk about that in just a second. And then lastly, it will be less rigid. So it's going to be a lot weaker than our crystalline. Some examples can be glass, waxes, plastic, etc. So when we talk about a defined melting point, it's just trying to indicate to the fact that, when we look at diamond, when we look at, a specific metal, we know exactly what its melting point is. But the issue with glasses, waxes, and plastics, you can have different types of glass, you can have different types of plastic. So there really is no defined melting point because it's going to be based off a lot of different factors. Basically, what is that substance made out of? Is there more of this or this in its structure? And you can see based off that particulate level model to the right, you can see the crystalline has that ordered structure left to right, but the amorphous will be kind of all over the place, okay? All right, but yeah, the crystalline is all those atoms are right next to each other. That's what makes it more rigid. While the amorphous that you can, it has a lot of spaces in between all the other atoms, okay? Now, the structure of a solid is influenced by interparticle interactions and the ability of the particles to pack together. So knowing the different types of solids that we looked in Objective 3.2, that's going to help us understand the strength of the forces between the solid. Moving on to liquids, so the arrangement of particles. When it comes to liquids, they're in close contact with one another, but they're still going to be moving and colliding, okay? Unlike the solid, they're going to be right next to each other. The liquid, they'll be relatively close, but they're actually going to be moving and colliding a lot more. So the arrangement and movement of particles are going to be influenced by the nature and the strength of the particles. And so this is going to come down to polarity, is there hydrogen bonding, and temperature. All of these can affect the arrangement and movement of particles. Temperature in the sense that if we increase the temperature for that substance, that liquid, they'll be moving a lot faster, making it more polarizable in some senses. Polarity, knowing if it's nonpolar or polar, can help us understand, is there hydrogen bonding there? Is there a different type of intermolecular force? One other thing that I'm going to mention is molar volume. So we're actually going to talk a lot about it more in 3.4 and 3.5, but first, molar volume is taking into consideration the volume that occupies 1 mole of the substance. This actually can be used as a conversion factor if you know how much volume that liquid would take up if you had 1 mole of it. And again, this would be how much volume in 1 mole. Now, it's been a minute since we've talked about gases, but at STP, which that is standard temperature and pressure, I should probably just quickly put what it means. Standard temp will be 273.15 Kelvin, or you could say 0 degrees Celsius, while pressure will be 1 atm. So at STP, this is a true statement that there's 22.4 liters per 1 mole, and that's based off our ideal gas law, and we'll talk more about that in the next couple of objectives. But overall, just trying to use that as a conversion factor will help us understand that liquid and how it behaves, okay? All right, gases. So in the gas phase, the particles will be in constant motion. So their frequencies of collision and average spacing between them are dependent on 3 things: temperature, pressure, and volume. And so let's talk about how all of these will be affected. So here, how are collisions affected with temperature? Well, if we increase the temperature, we're going to be increasing the speed of our particles. So this will increase the number of collisions between those particles. Now, when it comes to pressure, if we increase the pressure, which remember pressure is going to be the force exerted by the particles on the sides of the container. Here, that means there should be a smaller volume. So here, more collisions. Pressure and volume are going to be going hand in hand here. And then for volume, if we have a smaller volume, we'll have an increase of collisions because they're going to be in less of an area together. And so there's going to be more opportunities for them to collide compared to a larger area. All of this will be used vice versa as well, if you wanted to do the opposite to see how collisions would be effective for a decrease of collisions. Now, because of this constant motion and minimal effects of forces between particles, a gas has neither a definite volume nor shape. The reason we say this is it's very hard to figure out the true volume of a gas. And so the reason we talk about this is gases, when we think about where they are at, they are very, very, very far apart. So here, if we try to decrease that volume as much as possible, then our particles are right next to each other, just like how a solid is. So to really get the true volume of a gas is very, very difficult, and we will actually be looking at in the next couple of objectives when it comes to gases. But just kind of know that we don't really know the definite volume nor the shape of a gas. Lastly, I do just want to say phase diagrams will not be on the AP exam. So if you end up looking online on phase diagrams, you've gone too far. Don't worry about it. Okay.